Okay, so this time let's actually look into like some actual papers and stuff and implement the particle simulation that we tried last time. But yes, this time successfully, of course. So yesterday I looked over this multi-particle hydrodynamics thing, and I found this paper which has a lot of math, but we can go through this thing step by step and try to implement each thing to get our simulation to look nice. And so far I've just reset everything to just having the positions and being able to reset the simulation. And yeah, like let's start from this point and then see where we can go from here, like by using the paper. So right now we have only the positions as vector 2s. Let me just do like a commit for the start of this part, and yeah, let's take a look at what we can actually do. So I mean, pretty much on Wikipedia and this PDF there are the same things. So yeah, let's go through this paper then. So this is like called fundamentals. Like these are the initial things that you might need to know. So here it shows like some weird math stuff. We don't really care about this. If you scroll a bit down, we find the actual useful stuff, right? So we can really use integrals and things like continuous in our computers. We have to use sums, right? Like the discrete version. And this equation here tells us how to compute like any property of our fluid or particle simulation thing. And for example, we will need to calculate the density. So let's imagine that A is anything, but for us could be the density, right? And how it works, we need to do a for loop over all the other particles, yeah, and compute this thing for each particle, right? So this is the mass, this is the property that we want to calculate, but it's on the other particle. Then we divide by the density of that particle. So when we want to calculate the density, these two things, I mean, wait, I can actually, because it would be easier. That's nice. Okay, so this thing and this thing would cancel out, right? So when we try to compute the density, so it would be bit lower on the page. And then this is like a weird function that we might need to just copy paste from here. Not really need to understand it, but it's like how much influence would this particle have on our particle based on the distance. So this is position, but it's called R for some reason. Yeah, so then here it says that if you want to get the derivative, whatever that is, you have to derive, it's more like the gradient, but you have to derive both this and this. So yeah, that's something we might need to keep in mind, but not that important. This is also something that I've seen it was used, but it's like if you have, I mean, you can see that here. Well, let's rewrite it. Yeah, like maybe this is something that we see a lot. So it's just I have no idea how to say like open the parentheses or something, right? Like first you multiply the first one and then you multiply the second one. Like this is just the distribution over some or yeah, whatever. It's for derivatives, I think. Anyway, it doesn't matter. So yeah, this is the kernel function that I saw is being used, so why not let's just use it, because if it's in the paper then it works. So we'll implement this one, and yeah, basically we'll also need to derive it like you saw here. So since it's in the paper, we might have an easier way to get the derivative. We won't have to brainstorm it ourselves. Right, and here is the example for density, how it looks like. So it's like I said, this term here disappeared, right? So yeah, basically this is what we want to compute at first, and maybe try to display this density of each particle, see how it looks. So yeah, I mean this is the first step, right? So first, let's get this kernel function implemented. So it's yeah, it's basically gonna be called, so it's gonna return a float, I think. Right, it makes sense to return a float. Kernel function, and it's called a Gaussian kernel function, and it should get the h, which is the distance between the particles, float x, and float h. So I think Copilot already knows, maybe 1 divided by h times 2. Wait, I mean it's almost there, but it's not quite. So here we only have, it's 1 divided by h times this thing, and then it's x, and it's here it's 1.0. Yeah. So I think we need math for this. So let's include math. So basically the Gaussian kernel. So we have the position. So x was the distance. Yeah, and then we can just do this density function. So we will need float particle densities. Create a, wait, it's not a, let's I mean that doesn't matter if we initialize it to 0. We could set it particle densities to 0 here, and also in the restart. I mean, sure, fair enough. We'll have a structure, maybe, for a particle, but for now, let's just keep things simple. And yeah. So we could have a function, right? That particle density, compute particle density, and we are gonna have, well, I think I want to have that structure at this point. So let's say structure particle. So we are gonna need position and density, and let's do that. Particles, and yeah, particles I, and we can actually use the, oh my god, okay, anyway, I mean we can also have a function to initialize this, but yeah, sure, fair enough, why not? So let's have void particle init like this, void particles, yeah, particles init, something like this, and then we can init them here. Okay, so let's continue now. So here we might want the particles. I was just thinking, how about having a structure particle array, which is gonna have the count and the capacity, and this will be items. Just because we have, if you know, right? Particle array, because we have, one sec, particles count, and here should be particles dot items. Well, I mean, what? Yeah. So particle array struct particle, okay, like this. So this thing we can actually initialize anyway. So I wanted to say, if you already know, I mean basically we have that DA append, it works for that, right? So here let's say, so it looks like this float h thing is like a config. So again, how about I mean, since I mean it's just a config, it's whatever. Ah, let's just say PS here. And here we need to use the address. Okay, it's fine. Let's use blue. I mean, we can also use white. It looks strange. Anyway, so basically to get the, well, it auto-completed anyway. So we start with a density of 0, then we have to do a for loop through all the particles, and I is the index for which we want to compute the density. So basically, if I is not equal to j, or I mean if I is equal to, it's the same thing, depends if you want to use continue or not. So right, so we need the mass of the particles, also this h thing. So yeah, I mean the mass will be constant, the h will also be a constant. So I was maybe thinking to have another structure for, let's say, the simulation config or something. So we could easily change the configuration. Right. So let's have a struct simulation parameters. So we are going to have h float particle mass, and for now I think that's it. We could also use defines and override them, but I don't know, that feels not sure about that, right? So let's just stick with a structure that we can pass in. Let's say here, let's say we also need float particle mass, right? We need to pass in some stuff. So then we can say struct. Oh yeah, and how about what if you want to see how this looks like? Well, we can use vol from alpha. It's like a really nice math tool. So let's do math input because it's cool. So let's say we have wx, and this is equal to h multiplied with square t of pi, yeah, like this, and then we have the like power e, and here we have minus and then a fraction, then we have x2, and here we have it should be again like a power h2. It's I think it's good. Anyway, if we now do like equal, it gives us some stuff, but well, oh no, it broke. So it's minus this thing x squared and h squared. So if you say plot h equals 1 or something, well, yeah, I mean it looks like this, right? Basically it's I don't know, it looks like a Gaussian bell, no? And if you say just plot, I mean this thing should have been, yeah, it's a bit broken. So let's go multiplied with plot h equals 1 again. But yeah, I mean, I don't know, yesterday when I was playing around with it, it was like in 3D. Oh, yeah, like on this axis, should be H, so you can see that it has bumps on that, and when it's negative it's the other way around. So if we have like 1, like if it's 0 it goes up to infinite, I think. That's why it's a blank spot here. So yeah. And this is a pretty nice website if you have math functions to visualize. Anyway, let's go back to the simulation. So here we initialize the parameters. Okay. And I'm just thinking, what if here we just send the params, right? Just send the parameters so we don't have to re-update that thing. So we are at the density step here. So basically, if let's do the easier one. So here we continue, and otherwise we have to get the distance. So we have to get the x basically, which is I mean, maybe this function does not exist in Raylib. So let's see, Raylib cheat sheet. So let's see, do we have distance? No. Magnitude? No. So yeah, basically I already have these Raylib extensions with functions that I didn't find. So let's take this and implement it for ourselves. But do we have like POW or SQRT? We don't. I mean, include math. Right, so it's just the classical distance. So yeah. So now we have this. It's nice. Okay, what's next on the list? So next would be to get the density itself. Maybe we do it directly. I was thinking to get the float in influence using the Gaussian kernel, and then just add it to density like this. So yeah, now let's add this thing to the update and call it to this thing. So here, when before we are drawing, we should compute the particle density. But let's make an update function maybe. So void simulation step. It should get all the particles in this thing, and the first thing is to just compute the density. So yeah, we won't see anything, but let's try to visualize density, right? And we can do that by changing, I guess, the particle radius. But first, let's see the the density. Let's see what it looks like. Wait, what? It's already declared? That's so strange. Like vector to distance is not here. Let's look. Ray lib GitHub. I mean, how do we get it then? It's in Ray math. Oh, maybe we need to just import Ray math. How does it work? Include Ray math. Okay, then we don't need this thing, I guess. Okay, let's see what's in Ray math. So we need to define this. Okay, let's also look Ray math sheet. Okay, so vector to distance. Oh, it's here. That's nice. Do we also have random float? No. Okay. So we have vector math, and pretty much that's it. That's good. Okay. I mean, it's enough for me. So let's. Should we just do this? Okay. Yeah. So here the density is set to always to 0. CMake. Let's try this thing again. But how can we make it see that this function actually exists? Okay, anyway. So yeah, for the density, we get the distance, and we get back the density. So, I mean, it's really annoying me. Really help. Yeah. Hmm. Maybe we can see that on uh, parameters, or what was it? Options. Options. It's not here, so I have no idea. Anyway, we'll deal with it. So what do we get here? Let's see. So we get something, some huge number. That's not good. Because the distance cannot be this big. So wait, how do we... Maybe I made a mistake here somewhere, and okay, configuration. Doesn't really say how to use it, right? I mean, in the examples, maybe. Yeah, I have no idea, but it looks like somehow maybe this thing doesn't work because those numbers are not really, don't make any sense, to be honest. Right, they are too big. It looks like doesn't make any sense to have numbers that big. Given that our particles are between what 0 and 800. So I have no idea how to... Hmm. Let's see into maybe raylib.h if it's included here somehow. Rayma? Not really. But when I tried to import Raymath, it was complaining. So I forget to... Oh, actually what I didn't do here is if not define maybe this somehow broke something. Because I don't get how because I don't really get how that doesn't work. If we just import RayMath, that works. If we just import RayMath. Really strange. Anyway. Yeah, weird. So now we actually get it looks like it's the right values, right? So let's try to maybe printf the density here and see what we get. Sometimes it's 0. I guess what the influence is really small. Let's see. Alright, it's interesting. Maybe maybe this thing is really small. Not enough particles. Yeah. Let's try to use a different H. So I saw that with a smaller H, it should increase the or should it be larger H? Yeah, with the larger H, it actually makes more sense. Okay. So now, instead of, or at least let's multiply the radius with the density, right? Let's try and see. Times particle density. Pretty small. So let's try to increase H to, I don't know, 100. Yeah, somehow it looks better, but let's make this blue. But see, like, where there are more points, they look a bit larger. Let's try to do the radius, like, what, 20, I don't know. Yeah, this makes it look a bit better, and I know that there is a cool function. Let's go to the cheat sheet. Draw circle gradient. The only issue is that it works with integers. So actually, let's go back to the Raylib. Let's search for it. Which one? I think this is the function. So my idea is let's just copy paste it. Okay, let's go into the extension. Okay, and let's just have it here, right? But let's change this to float. Yeah, I'm not really sure why. Or let's make it work with vector to position, because he has here draw circle V, so maybe we can have draw circle gradient V, right? Like try to keep the, well, we don't need to include relief here. Okay, so we have we need some stuff from here then. Not sure what, but let's see if that works. And here we can use position X and position Y. We can have position X, we don't need that. Here we can have position Y, position Y, position Y again, and here we can say position X. What do we need? Math? Maybe. Okay, I guess. So let's see if this works. Draw circle gradient V. So we need another color. And I was thinking, well, let's see how blue is defined. And what if we try to, wait, do we have transparent as a color? No. Oh, blank. That's, I mean, whatever. Let's do from blue to blank. I mean, somehow it makes sense. Let's see. And this looks better. I don't know why it's flickering. Maybe it's because it's recording at the same time. Couldn't be because of other stuff. So yeah, I mean it looks like it makes sense, but it looks like some density. So yeah, strange. So yeah, the density makes sense. I guess we can have a commit here just to say that feature display density, just in case we want to go back to this or someone wants to look at the density or something. Okay, so then let's go to the next step. We have the density, right? This is like something for speed, but I'm not sure we need it right now. Like this is for speed, right? So other stuff. But what we are interested now basically is to get like something related to pressure maybe, because we have this thing right here, which is like the momentum, which is the acceleration basically. It's the derivative of the speed, which is acceleration. So this gives us like how much force we need to apply on a particle based on the other particles, and for that we need the pressure. And yeah, I haven't found how they calculate the pressure in here, but I found I don't know if it was on the Wikipedia page. I think it was, yeah, it was here. It's like called Cole equation to get the pressure. So we can use that thing. And it's basically, I mean, if you think about it, it's just the density for some reason. So yeah, more or less. So we get this momentum thing. Yeah, which maybe makes sense. The contribution to the force of particle A. Oh yeah, and here it also gives us like if we use that Gaussian part thing, it gives us the derivative. So say if it here comes like the h squared, the thing, and I think also 2 is from there. And mb is just because you multiply this with the mass to get the force. You multiply acceleration with mass, get the force. So with ma. Yeah, I think something like that. And yeah, I mean this is some more stuff. I have no idea what. I mean, it looks like the same thing to me, to be honest. And yeah, basically I think this is like how we get the force of a particle, right? Although the only thing I'm not really sure about is how we get the direction. Do we get it from this one? Because like, and I was looking at that here in this case, I always thought that W, I mean, it takes the X, right? But is it modulo? Is it not modulo? Like, I'm not really sure. But the density is a number, so it should be modulo, right? So maybe we get the direction. Where was it? We get the direction from this thing. This gives us the direction of the force. So yeah, maybe this is one of the next things we need to do. Probably also the pressure. So let's see the pressure first. So compute particle density. Let's have float compute pressure. And we need some stuff. We need density, rest density. It float rest density. We also need this thing. So let's go to its page. Adiabatic index. Although I think it should be an int. No, I mean it could be a float. And we also need the speed of sound. Yeah. So float speed of sound. Well, I would still like to see the density here. or maybe get like average density. Because let's see, float average density, let's get it printf, because I'm curious, like, okay, so we can use 1 as the rest density then, maybe. If we make this thing 10, then what average density we get? It's much smaller. Interesting. If we make it 1000, okay, so it doesn't, see, it's really interesting, it doesn't increase over 1 or something. No. Okay, I mean, let's make it 1, the average density, like the target density or rest density. Okay, so go here. We need the rest density. I mean, this is what's strange, because it makes sense to make it 1000, but we might need a multiplier for density, because let's say the distance, we take it in meters, right? When we do all the computations in physics and stuff, it's in meters. But I mean, for us it's more like centimeters, right? We imagine that it's really small. So let's do something like x equals x times 1000 0f, convert to we imagine that the distance our screen is in centimeters, right? So we have to multiply by 1000. Oh my god, I deleted the average, so float average. Okay, and let's see again the density. So if we multiply by 1000, oh my god, we have to divide. I'm sorry about that, I don't know how to. Ooh, that's perfect. Okay, and now we can make the particles small again. Okay. And if we let h to be 1, it's almost it's almost 1000, so it's perfect. So let's make the particle radius really small, like 0.002 f or something. Let's go again. It's too small. Let's make it like this. I mean, it's decent. So now we are closer to like real stuff, I guess. If we make this larger, then yes, see, now the density drops. Interesting. Let's see more stuff. Yeah, but now like it looks like density is the same everywhere. Doesn't matter that much, to be honest. So let's leave it like this for now, and let's do the pressure. So first thing, let's say we compute the B. Like if we open this, that's called B. So let's get the B thing. It should be res density. Yeah, it should be like that. Then we need to do the inner thing. So let's float div. It should be, well, I don't know how that thing is called. Well. Let's do that to get the thing from inside. And but here it also adds some P0, which is background pressure. Let's have it. Float background pressure. But I mean the background pressure is pretty much to not have negative pressures or something. So let's go ahead. So I have the adiabatic index 7 for water. Speed of sound. Well, I was looking at this speed of sound, water, and it's like, I mean, let's give it 1000. And ground pressure, water. Do we have? Yeah, makes sense. Anyway, I don't think it matters that much. So let's go into the simulation step and do another for loop, and this time get the pressure. And oh, of course, let's put the pressure on the structure. Let's put the pressure there, so we can actually initialize the pressure like this. Yeah. Okay, let's put the pressure now. Like, doesn't matter, it's called density or whatever, and it's negative. What a surprise. So let's use like a larger number. Let's do like this, but let's make everything 0. So it's like 1. Wait, can't we? We can't. 100 million. So it's 100. Anyway. So now it's positive, right? Yeah. Now it looks positive. Let's see on the thing what is next. So next would be to compute this force. I mean, we'll have to play around with this until we make the simulation look nice, but let's see. So we have the force. And then moment acceleration. we can ignore MA then. I mean, although it's 1, so it doesn't matter when we get the acceleration, because it's like easier to apply the acceleration on the speed, and everything should move after that. Oh yeah, this thing moving the particles, right? This will be after. So let's see how we move them actually. So it's just with speed or by using the SX factor. So it does an average and whatever constant. So it just uses the speed. I think I saw somewhere like what was VAB. It was like, I think it's the difference between VB and VA. Okay, and what is 3.9? Well, we did like this, right? To get the oh yeah, here it was VA minus VB, but yeah, we computed the density like that, not with whatever. So I guess the next step is to just get the velocities going. So let's go ahead and probably just add here structure velocity. I don't think we need anything else because the acceleration is computed each time. So yeah, let's see. Let's do structure vector 2 compute. It should be like momentum or pressure force. I mean, I would say yeah, I mean, it's pressure force basically. But I think we might need just the momentum to be able to get this thing. So let's call it momentum. Right, and here we need, let's just generate stuff, and yeah, basically we have the particles, the particle for which we want to compute the momentum, and some parameters. So let's reuse this thing to get the derivative. We just have to believe that it will give us the derivative. Okay, here it is. So yeah, this is the, basically if we have the Gaussian kernel, we can say float Gaussian kernel function derivative. It should be minus 2 times x, yeah, divided by Whoa, that's crazy. It's exactly that. Although the issue is that I think that in this case this should be like a direction. Right? It should give us the direction of the woohoo. Because the kernel function itself gives us just a number, but yeah, like let's say in this bad boy article, yeah, here it uses this thing, but do we have anything like derived? Here it looks like it uses the vectors, right? And that's the feeling that I get from that formula. So what if here we say vector 2 and here vector 2. Oh, it's vector 2 length to get the magnitude. Nice. Okay, so let's say we have the x is a vector in this case, right? And then we have the float h, right? So when we do this thing, let's actually just do return vector to scale. I saw this thing. Scale vector multiply by value. Okay. So you give it the vector and the value. So it should be, it's pretty strange. Let's see, because last time it was fine, but we just needed to do here, we need to do something like this, right? We need to multiply x minus 2. So if we look back at this thing, we have x, we have minus 2, h squared, and then if we look at what remains, it's basically the thing from before. So it's the Gaussian kernel. So it's basically that. So yeah, I think it's decent like this. And I think it should be decent. Because this just gives us the derivative, it's not huge deal. So Okay, it was here. Alright, like my only concern is that here we were dividing by 1000. So it's just that not sure if that should be done maybe in here. So let's change this thing to get also a vector to x, and then let's have something like float x length. Let's divide by 1000 x length, and yeah, basically we no longer need that. Do this thing, and in this case let's do vector 2 subtract, and here we can say vector 2 subtract vector 2, or we can just say vector 2. That's really good because I didn't realize it was type def. Okay, so yeah, for the Gaussian kernel, now we do the computation of the modulo here, and we divide by 1000 in only one place, right? Because we want to do like in centimeters, or we imagine that our screen is in centimeters when we have to convert it to meters, right? So we divide by 1000, or I think it should be by 100. Anyway, is in millimeters. Let's not talk about it. Let's say that it was millimeters all along. Anyway, yeah, and the derivative would just multiply this x with the whatever kernel function. So yeah, the next step is to get the momentum. Right, so we can do the okay, let's so we can compute this thing. Let's see here, it's whatever. So yeah, pretty much doesn't matter, right? Like we get the same thing as down here. So let's get the pressure for both of them then. So wait, yeah, we need to do a for loop. Okay, let's delete that. So we need to get the momentum and return it. So we need to iterate over all the particles first of all, and we need to get the pressure. Oh, we have the pressure. We have it in the particle itself. So we need to compute these divisions, but one of them we can cache outside. So float, I don't even know how to call it, pressure div pressure A, let's call it, and do that thing. Float pressure B should be with J. So we have these two. Okay, we get the x vector, like this thing, or I mean what we're gonna pass to that, and pretty much that's it. We need to say something like vector to gradient. We pass the gradient, so we get the gradient. We need to compute this sum, so let's call it float pressure, whatever pressure. We also got this, and now we have to say something like float, no, it's a vector to m. It should be -1 times mass times pressure, and we scale the gradient with that, and then we have to add it to the momentum. So this should give us the acceleration, but like based on the other particles, right? We get the acceleration, and the last thing we need to compute now is the how much we move, basically based on the speed. So this gives us the momentum. We can store the momentum, I guess. On the particle, but maybe we just not do that. I'm not sure where it says how to modify the speed using, I mean, it's pretty obvious, but yeah, is it like this? I mean, thermal energy sounds like something that causes speed, but whatever. So equals 0. Let's say that we have the momentum. Oh, this is interesting. Let's see on Wikipedia. Maybe there's something that says how to move the how to change the speed. Oh. Wait, no, I mean, no. No, I was hoping that there's something like in this case. Well, maybe I'm just stupid. And let's get the delta time. Float dt equals get frame time. So I think here we should just scale, but I'm not sure why it divides by density. Because here the momentum, or like the where, I mean, we just did everything. I don't think we have to divide by density. I think it's enough to have dt here to get the velocities. Okay, and now that we have the velocity, we do another for loop, right? And we try to get this thing. But first, let's just do this, and hopefully it doesn't explode. That's the only thing. Yeah, it explodes. Maybe I broke something. Oh, that was just the pressure. Let's see the density again. Maybe something changed. So I mean, density is 1000. It looks good to me. Let's make these things one smaller. Pressure. So let's leave pressure in. Pressure is like whatever huge number. 60 million. No, 6 million. Yeah, it's 6 million. So it basically exploded. What I was hoping not to happen. So let's see. I mean, the density is somewhere around 900, right? So if we do 900 times 900, we get this number, and then we have somewhere around 6 million. If we do the division, wait, we have to divide twice. We get somewhere around 7. So these would be like 7 in the magnitude of 10, I'm thinking. Maybe the pressure is just too big. Or something. I mean, if I remove another 0, it's gonna be negative, I think. And it's still huge, but it's negative. And I think this is gonna break it. Yeah, it's like instantly breaking it. The momentum. I mean, everything is just from the paper, so let's see, printf pressure A. Let's just move this thing here and see what happens. So pressure A is pretty random. It is just randomly going at it. So let's see the momentum. Momentum itself. It's too big. It's really big. So like even if we divide by density, it's still huge. Maybe the delta time is not that great. Maybe we need to set the delta time ourselves to like something really small. Like let's say the simulation step should be like something like this, like really small. And let's see the velocity. Like we have the momentum. Let's see the velocity that we get from that momentum, right? And the velocity is wow, this is insane. I'm pretty sure that this looks like an error, but it doesn't make sense. From this thing to get this thing. Because it's just multiplication. Wait, oh no, I did some... Wait a second. I don't think I should add. I think it should be just this. The velocity, right? I mean, I'm not sure. I mean, it looks a bit better, but I don't think, yeah, I think it should be just... Wait, I'm not sure. This makes me question myself. Because if we have like the acceleration, we need to update the velocity. Let's see, let's try to do that. See, like see now it changes and it's a bit better. Wait, why does it go towards the center? But I mean it's painfully slow. I guess it's just the frame rate. It takes like almost 1 second each frame. Let's put less particles. Let's put like only 256 particles. Oh no, oh my god. Okay, let's not move then. Maybe there is a minus sign. That's... Oh, and the density is so small. Wait, there's the pressure. Because I'm thinking that the density should look fine. It's only 100. Interesting. if we make the particles smaller size, doesn't look like it changes anything. It actually makes it, let's increase the size then. Okay, I mean, yeah, whatever. Like, see, when we move, like now it's doing something else. Yeah, for some reason the density is acting strange when we change the number of particles. Right, like something needs to be normalized, I think. Well, I mean, I know the density should be normalized in some way. I mean, let's try to put more particles, something. Yeah, again, they still move towards the center. I mean, because it makes sense, I guess, to try to increase the density to 1000, right? Like that would be the goal of this thing, to try to get the density to 1000. And here, for example, it was larger than 1000, so it started to push out the particles. So, I mean, it basically it works, but it's more like a gas. And yeah, the problem is that something needs to be normalized there. Because regardless of the number of um, particles and the mass, regardless of this, of the mass or the number of particles, we should get the same density or something. Although, I mean, it makes sense that if we have 256 particles of mass 1, the average density, or I mean the total density, will be 256. Yeah, I mean, we can try to implement the other movement. Maybe that changes anything. So that was this one. So it's basically, let's try it. So let's do compute vector 2, compute should be movement, I guess. movement, yeah. And here we should get all the particles. Okay, we have VA. Let's have an epsilon. Epsilon. So epsilon should be between 0 and 1. Okay. So if I is equal to j, we continue. And we have basically the movement is equal to particles items velocity. We start with the velocity. Okay. And then we have to do this addition. So like before, we get subtract to get the x. Then we need, of course, to get, well, here we just get the influence, but it's not the derivative, it's the kernel function. Oh, no, sorry, it's a float. It's the influence. Then we need a float for average density. Then we need the VBA. So vector 2 V is actually, but it's the other way around. It looks like it's J first minus I, and then we need to multiply the influence. So let's get the fraction then. So vector 2 should be like, let's call this thing VBA. Then V should be VBA multiplied with influence with mass and divided by density. Yeah, like that. And the movement we add. Yeah, it makes sense to start with 0 actually. 0, 0. And then we say movement. We scale this thing, and then we have to add the particle item velocity to the movement, just like that. Although I haven't used it, compute movement. So movement, and here we need to use movement instead of velocity. Okay, and let's see what happens if we increase the mass. And I mean, it moves differently, but man, it's so annoying that I can't figure out fast enough what would be the solution to make the the density behave right. Like maybe there is something wrong in the kernel. When we get the influence, Yeah, I'm not sure. I mean, strangely enough, it kind of makes. Yeah, I don't know. Like if you have very few particles, it makes sense that the density is small. Like if you have only 10 particles in a, let's say, inside a volume, the density will be smaller than if you had 1000 particles. So that's correct. Okay, so how we compute the density is fine. Then maybe when we compute the pressure, we should think more like trying to normalize this thing, because the pressure is what's annoying, because it gives like such random values. Maybe it's like the speed of sound, right? Should be changed based on the number of particles, because it, I mean, it changes based on the density. Like this should be a function on density, right? Um, so yeah, basically this would change the pressure if we take this into account. Then what else we have here is like, I mean, just the particle density divided by the rest density, because we want to get to the rest density. That's the point. So this cannot really change. Well, we do a -1 for some reason, but like this thing will always be negative. Well, let's think about it. If the density is larger than the rest density, it will be positive because it's greater than 1. But if density is smaller, x will be negative because it's less than 1. Right? And I mean, the adiabatic index just magnifies that discrepancy between the densities. So it's I mean, it's fine to use it. Like this makes sense, right? It gives us the direction of the pressure in some sense. If the density is too small, the pressure is negative, then we need to wait. If the pressure is negative, we need to what? Expand, or like fall onto itself, basically. That's what we need to do to increase the pressure. And if the pressure is too large, we need to like expand. So that's what x does. And b is just like a factor. So I mean, even then, this thing is okay-ish because it gives us the direction of the. It gives us either we expand or we do the opposite of expanding. I don't know the. Is there a word for that? No idea. Anyway, and when we compute the momentum, let's look again at the formula for momentum. It was this one. We basically take the pressure of A, we divide it by, I have no idea why it does this, but whatever. Like if we divide the pressure by the density, this thing would make sense that somehow this would cancel out with this, in some sense. So it's pretty much just the pressure itself, maybe scaled a bit down. But like the scaling is proportional, so if the pressure is really big, then the density will be really big in like that idea. So this thing shouldn't be like insanely weird, like an insanely weird number, right? It should be decent. As for this one, the same thing. So then we get the delta, whatever this is called, the derivative of the kernel function, which is just a Gaussian, like it's just like a bell like this. Like for example, if we have this thing, if you are on the x-axis like really close, then it changes slowly, then here it changes like, I mean decently, I don't know, rapidly, and then it starts to change like slowly again. Like maybe you saw in the simulation, if you look, it starts out, or at least here it moves like really quickly, but you can't see anything because it's too small. But it moves out like really fast at the beginning and then it slows down, right? Like that's because of the slope of the kernel function. So yeah, that's one thing. So I mean, even the compute momentum it looks fine. It gives us basically the direction in which we want to move. And then we have the compute movement. Then we have the compute movement, which is just this one. Yeah, I was thinking that maybe something we can try to do is to compute the rest density based on the mass, the volume that we have available, and what else? The number of particles. So we know that we have, let's say, 1000 particles. Each particle has mass 1. So it means that the rest density should be 1000, right? Something like that. I think. Like let's say we put here for rest density times number of well, what was it? Particle count, right? Maybe this would change something. Let's see. Oh, yeah, this makes it so it's not really good. Okay, now it exploded. So let's keep it at 1000. Okay, anyways. Let's see what happens if we leave it. Let's do more particles, like 512 particles. Okay, it explodes pretty much. So let's add back the let's add the gravity. So maybe we can have gravity here, like float gravity. Right, and So we have the momentum and the vector to gravity. Let's just add it. So now it should also try to fall down some way. Let's do less particles to 56 if you have the mass that large. I mean, this one starts to fall down. Anyway, let's try some more stuff. So let's do also collisions with the walls. So here we have the movement. Let's say the vector to position is this one, and then if position is less than 0, we set it to 0. But see, like, I mean, the weird thing is that here we set the velocity, we don't update it. Right, which is, I mean, to be honest, I think like it should be, we should be adding to our velocity. What if we say here just gravity and take a look at what happens? Well, we need to make that's okay. Let's go back, and here let's put just gravity. Like make the particles fall down. The wrong command. So like they barely move, right? So equals. But if we add it, well, I mean, compute movement here is not the one that we wanted. So movement is, let's say, just velocity. Wait, what? Wait, did I do something wrong here? Strange. Wait, isn't velocity like velocity plus acceleration times delta time? What? Okay, let's do something like 0.1f. Move it really slow. And yeah, I mean, it's something wrong. But how? Like, why is it sometimes movement is such a weird number? Velocity we just change it here. Hmm. Oh my god. I forgot to initialize the velocity. um, right, like I didn't initialize the velocity or where is it? Inside of this thing. Yeah. Well, let's say actually here. I was like, what the hell? That's why I didn't work with addition. Now that's embarrassing. Okay, now it looks better. Maybe, oh my god, if that was a bug. Yeah, I'm not sure why it does. It always tries to push that density thing. So now it looks better if we do 0.001f. I forgot how much it was, but anyway, let's see. So now it looks better, but if we use this movement, well, I mean, it still looks like it falls down. And if we actually do momentum here, momentum. Come on, come on, come on. Oof, oof. That's that still sucks. Well, maybe we just have to do this like really small number. I like have a really small step here. Yeah, and if we have collisions, maybe that helps. So let's try to say something like vector to position. If position is outside, let's have here a float damping when we collide basically. 0.9. Like when we collide with a wall, we lose some of the speed. So particles times damping. Oh yeah, that's all. And this one, and then for y. Oh, and then for y. Wait. Yeah, like that. And then we just set the position. So let's see. Oh, now it looks better. But I mean, now it looks much better than last time at least. But it's still like empty space in the middle, which is not occupying. So let's see if we decrease this step. It becomes yeah, like not sure how we can do that. Oh well, let's try to add more particles. Yeah, and I mean basically we just showed the density with yeah, but as I said, like when we increase the number of particles, like the parameters change. So yeah, like not sure how we can do. Even here, like the density is too small. Like when we have a lot of particles, the particle density is too small. Let's take a look at the influence. Let's say when I equals to 0. Let's look at the influence. So it's like 0.5, 0.4, something like that. And what if we have less particles? 100 particles. It's the same value. If we have 500, it's a bit less. But I mean, it's still around the same. So I don't know. Like why the average density becomes that small. And let's see. So it's 250. If we have 100 particles, it's like what? It's just 50. If we have, let's say, only 10 particles, it should be. And in my case, it's gonna be 5. Yeah. So so for 1000 it should be 500 at the average density. So maybe should it be like 5, 0.5? Yeah, like half the number of particles, but divided by 2.0. Let's put like 56. So for this one it should be around 120. Yeah, but we cannot really see the particles, they are too small. Let's say the radius is larger. I mean, at least this looks interesting. Okay, it's too large. 0.1. Hmm. Well, at least now it's a bit better. Let's increase the gravity. Let's make it 10 times larger. Wait, what? Do we need to make it like... Wait, is something wrong with the gravity? Not sure, it looks weird. Let's see the momentum. Oh, it's like huge. So let's do this one also, like really big. And apparently it's not enough. Even larger. Oh, wow, let's just, go insane mode. Yeah, I mean it has really low FPS. Okay, and the damping could be also like 0.3 maybe, something really small. And now oh no, I get flashbacks from last time. It gets in the same position. But I mean the gravity was too big, probably. Yeah, well, I mean I'm still not sure how to get this thing to work like really well. It's probably just trial and error. Because yeah, I mean I really was trying to copy the paper as much as I could, but yeah, it's just strange. Let's try to play around with other parameters, see what happens. Like I think if we increase the speed of sound, it might propagate faster, like all the pressure information and stuff. And if we try to decrease it, what might happen? It should be like slower. I mean it's interesting. Let's try to also increase the damping. Yeah, like something, yeah, still not that great about the simulation, but this was 1000. Maybe try to change epsilon. Say like it. I mean, yeah, I mean it looks more interesting than last time, but still a bit strange. I mean, it's cool just watching it, trying to figure out what would happen next, but yeah, we. What if we created life? No, just badly implemented simulation. Yeah, like it would be worth to try and play around with different kernel functions and maybe see if that helps. Maybe I did maybe I have some bug in the code that I can try to check and see um, what could be a mistake in there. Like maybe I missed something from the paper when I went through it. Because yeah, I mean, I mean, I have no idea. There are no, well, at least I haven't searched how the results look like for the paper. But and I mean, it's pretty old, so yeah, like you'd expect to get something from this. So yeah, like I mean, the main idea is trying to get like of this paper is trying to get the rest density to be basically average, let's say, or something like that, like filling the entire space. But yeah, not really sure where it gone wrong. So okay, let's. I mean, pretty much that's the attempt at it. So yeah, like let's see. Let's try one more time. Let's increase this. See what happens. Hmm. The average density went down. Basically, I think h, looking from this picture, gives us like the influence radius, let's call it. Right. I mean, it's really slow. Not really because of the FPS, I guess. It's more because we manually put the delta time, so we could actually increase the speed, I guess. Oh, make it even faster. No. Let's leave it like, well, let's try to use get frame time. Oh no, it was too fast. Yeah, then let's manually set it so we can actually see something, right? So like we can try to see what happens if we change. I mean, in the end, we still get back to the original problem of stuff just settling down. Let's see if we change the background pressure. Still the same stuff. What if we increase the epsilon? Oh, increasing the epsilon somehow did something. But it looks weird. Let's increase the damping. Huh, well, I mean, it looks a bit better like this. What if we decrease this level without that much gravity? I mean, yeah, let's see what happens if we put more particles. Oh no. That was looking cool. Yeah, I maybe should have put these parameters in the same place. I wanted to see like to view it better. I don't know what to say about that. 512. Like 512 looks enough. And yeah, for gravity it was decent, like this large. What else can we change here? Maybe make this larger. This makes it more agitated, something. So making it smaller would not what I wanted. So if we change the background pressure even more, yeah, I mean, let's see if we do epsilon small again. Interesting. it looked good for the first couple of seconds, but then it fell off. What if we go for something larger than 1? Yeah, in the paper it says that it should be between 0 and 1, so that's okay. So let's leave it 0.9, and let's try to do damping 1, so it just goes crazy. Oh no, it's gonna break. Okay, let's stop it because there's no loss of energy when it clashes with the wall, right? If we don't do damping. So it's just going at it. So yeah, I mean pretty much this is the how I copied the smoothed particle hydrodynamics paper. I would say that probably it should look better. Maybe I missed some stuff, but I think it's a decent result for now. I guess let's take a break from this one until I figure out how to do it, and then after I manage to figure it out, I'll also do the CUDA version. Like basically what we need to do is just, it would be pretty easy, like break each for loop into threads, right? And I guess I don't know, like homework as a meme, trying to do it with p-threads. I mean, I'm not gonna do it with p-threads, but if you want to try it out, I also make the repo available. So if you want to just try to use p-threads to have more particles, because right now more than 1000 particles is really slow. So yeah. Well, I mean, yeah, I guess let's say something like implement scuffed SPH, I think it's called. So yeah, I'll create a repo and see you next time.